Let's consider the expression that gives the directional derivative of f in the direction of u at xy. And right now I have f of xy just to say that it's in R2 and not R3. We can write this as fx times a plus fy times b. And I'm dropping the xy right now. We could envision this as being a dot product of fx, fy with ab. And this is just reimagining the expression that we have through the lens of a dot product. We already knew ab was a unit vector. Now we have this vector fx, fy. It turns out that the vector fx at xy, fy at xy, which can also be written as the partial of f with respect to x times I plus the partial of f with respect to y times j, is an actual thing. It's an actual vector. It's called the gradient vector. And it's denoted with an upside down triangle with a vector arrow on top. I am not making this up. fxy. And we'd say that this is what we just wrote. fx of xy, fy of xy. That upside down triangle with f, it's pronounced del f. The upside down triangle vector itself is called the del operator. That's del. When the del operator acts on a function f, it says, hey, take a partial with respect to x, take a partial with respect to y, make those the components of a vector. R3 is what you think it would be. It's just fx, fy, fz, still a vector. What's an operator? An operator is the thing that acts on functions, right? We see that this is a del f, and it's got vector notation to let you know that the result is a vector. You've seen operators before. A derivative is an operator. An integral is an operator. They're things that act on functions. With that out of the way, let's go ahead and look at an example. For f of xy equals xy cubed minus x squared, find the directional derivative at 1, 2 in the direction of theta equals pi over 3. Well, we need two things. We need the pieces of del f, the partial derivatives, and then we need the vector associated with theta equals pi over 3, the unit vector, that is. The partial of f with respect to x is equal to y cubed minus 2x. The partial of f with respect to y is 3x y squared. Yeah, we're good. The partial of f with respect to x evaluated at 1, 2 then is going to be 8 minus 2, 6. And the partial of f with respect to y evaluated at 1, 2, there we go, is, looks like 12. So just to put this together with what we saw before, del f is equal to, in this case, y cubed minus 2x, comma, 3x y squared, and del f evaluated at 1, 2 is the vector 6, 12. The unit vector u in the direction of pi over 3 is going to be the cosine of pi over 3 sine of pi over 3, and so equals 1/2 square root of 3 over 2. Expressing the directional derivative of f in the direction of u at 1, 2, I know that's kind of a lot, we get that this is del f dot u, and in this case we have 6 times 1/2, which is 3, 12 times square root of 3 over 2, so that's 3 plus 6 times the square root of 3. It's a number. It's a derivative. It's the slope of the tangent line if you're standing at the on the surface associated with the point 1, 2 and looking in the direction of u, which is theta equals pi over 3 with respect to the positive x-axis. But it's a slope is the bottom line.